Tower 2's water deluge system doesn't use pumps. It doesn't use water towers either. Instead, SpaceX built something that makes 422,000 gallons of water move faster than any traditional system could match. What replaced decades of proven aerospace engineering? The answer is nitrogen gas created on demand. Water flows through massive heat exchangers, while liquid nitrogen boils inside them, instantly generating enough pressure to blast water through the flame trench in milliseconds. But here's what really shocked the industry. Could this same system scale up to launch 10 starships per day? Here's the thing about traditional rocket launch pads. They're stuck in the 1960s. NASA's water towers at Kennedy Space Center stand 300 feet tall, holding millions of gallons just to supply enough pressure for a single launch. The pumps needed to move that water consume enough electricity to power a small town. And when something breaks during countdown, you're looking at hours of delays, sometimes scrubbing the launch entirely. SpaceX learned this the hard way at LC-40 back in 2016. Their Falcon 9 pad used conventional pumps, the same technology everyone trusted for decades. Then came the launch accident that didn't just destroy the rocket, but damaged critical water delivery infrastructure. Instead of rebuilding the same system, Elon asked his team one question that changed everything. Why do we need pumps at all? The answer they came up with sounds absurd until you understand the physics. Take liquid nitrogen, cool it down to negative 320 degrees Fahrenheit, then let it warm up. When LN2 transitions to gas, it expands 700 times its liquid volume. That expansion creates pressure. Massive pressure, enough to move water faster than any mechanical pump ever could. And because you're generating this pressure thermally rather than mechanically, there are no moving parts to fail during the critical seconds of engine ignition. So SpaceX rebuilt LC-40 with nitrogen pressurized tanks instead of pumps. Load the tanks with water before launch, pressurize them with nitrogen gas, and when the countdown hits 0, that pressure forces water through the deluge system instantly. No motors spinning, no electricity surging through pump houses, just physics doing what it does best. But that was just the prototype. When construction began at Starbase, SpaceX faced a problem traditional launch sites never encountered. Starship isn't just bigger than Falcon 9. It's 33 Raptor engines producing combined thrust that makes the Saturn V look modest. The heat, the acoustic energy, the sheer violence of that much combustion happening simultaneously meant their water system couldn't just be good. It had to be perfect, every single time, without maintenance crews babysitting equipment between launches. The Pad 1 system took the nitrogen pressure concept and scaled it up dramatically. But they still had a bottleneck, filling hundreds of nitrogen gas tanks hours before each test or launch. The logistics were manageable but inefficient. What Tower 2's system does differently is generate nitrogen pressure on demand, exactly when needed, in the exact quantities required. The deluge farm now includes massive heat exchangers that work like specialized radiators, except instead of cooling something down, they're designed to boil liquid nitrogen instantly. Water circulates through these exchangers at high flow rates, while liquid nitrogen flows through tubes inside them. The water's heat transfers to the LN2, causing it to vaporize almost instantaneously. That nitrogen gas shoots into the water tanks, pressurizing them in real time as the countdown proceeds. This gives SpaceX something no traditional system offers: dynamic control. You can modulate flow rates on the fly. Need more cooling on the flame diverter as engines throttle up? Increase the nitrogen gasification rate. Need to extend the deluge duration for a longer static fire test? Keep heating that LN2 and maintain pressure longer. Traditional systems are essentially on-off valves where you open them, gravity and pumps do their thing, and you hope the timing works out. The numbers reveal just how advanced this system has become. Tower 2 can move up to 422,000 gallons per ignition event, whether that's a launch, static fire, or even a booster landing. Most of that water, over 300,000 gallons, flashes to steam the instant it contacts surfaces heated to thousands of degrees. Another 17,000 gallons gets captured by containment systems for filtering and reuse. But here's what really matters. Unlike Pad 1, which required multiple static fires before each flight to validate the system, Tower 2's precision means fewer tests. SpaceX expects to reduce those checkout procedures significantly as they gain operational experience. Beneath the launch mount sits the integrated flame bucket, a double-sided, heavily reinforced steel structure positioned directly under the center of the booster. When 33 Raptors ignite, exhaust temperatures exceed 6,000 degrees Fahrenheit. The acoustic pressure alone can shatter concrete. That flame diverter has to absorb that energy, split the exhaust flow, and channel it down two paths in the trench without melting or cracking. The water-cooled steel plate on top of the launch mount adds another layer of protection, and unlike Pad 1's plate mounted underneath, Tower 2's sits on the top deck where it's easier to inspect and replace if needed. Then there's the dual booster quick disconnect system, where SpaceX took their "the best part is no part" philosophy seriously. Pad 1 used 20 individual Raptor quick disconnects, one for each outer ring engine, to supply ignition propellant. 20 connection points meant 20 potential leak sources, 20 inspection points, 20 components that could fail. Tower 2 eliminates all of them. Two large BQDs handle liquid oxygen and liquid methane separately, feeding directly into the booster's internal distribution system. Those BQDs retract faster during launch, getting clear of the exhaust plume in milliseconds rather than seconds, which reduces thermal damage and speeds up turnaround. The launch mount itself reflects this simplification philosophy. Where Pad 1's design was circular and compact, Tower 2's mount is boxy and larger, with a circular opening for the booster in the center. The rectangular structure makes it easier for maintenance crews to position work platforms, run cabling, and install new hardware as Starship evolves, and evolution is already happening with Block 3 Starship in development, which means the infrastructure has to adapt without requiring complete reconstruction. What makes all of this sustainable long-term is Starbase's air separation unit. Every Starship launch consumes hundreds of tons of liquid oxygen, which previously meant dozens of cryogenic tanker trucks making deliveries from distant production facilities. Supply chain delays, weather disruptions, road conditions, any of those could impact launch schedules. The ASU changes that equation entirely by producing LOX and LN2 on site through cryogenic distillation of atmospheric air. SpaceX eliminates external dependencies while scaling toward their goal of multiple launches per day. Construction began in July 2025, and by late 2025, the facility was already becoming a permanent part of Starbase's infrastructure. What we're watching at Tower 2 isn't just a new launch pad. It's a complete rethinking of ground infrastructure based on one principle. Complexity is the enemy of reliability. Every pump eliminated, every quick disconnect removed, every system simplified means fewer failure points and faster operations. The nitrogen pressurized deluge system shocked engineers because it violates conventional wisdom. But conventional wisdom was designed for launching a few rockets per year. SpaceX is building for a future where starships launch daily. That's not marketing hype. It's why every decision at Tower 2 prioritizes speed and simplicity over tradition. The nitrogen pressurized deluge system isn't just clever engineering. It's the foundation for something the aerospace industry has never seen: rapid reusability at orbital scale. Think about what Tower 2 represents. No massive pumps consuming megawatts during ignition, no water towers requiring constant maintenance, no 20 individual engine disconnects creating inspection bottlenecks. Just heat exchangers, nitrogen gas, and physics working exactly when needed. The system that shocked engineers when SpaceX first proposed it is now the standard they're building around. And as Block 3 Starship pushes performance even higher, this infrastructure adapts without major reconstruction. The real test comes in 2026 when Tower 2 handles its first rapid turnaround sequence: booster landing, inspection, and relaunch within hours instead of weeks. If the deluge system performs as designed, delivering 422,000 gallons with millisecond precision multiple times per day, it proves something much bigger than water delivery. It proves that rethinking everything, even systems that have worked for 60 years, unlocks capabilities everyone else said were impossible. That's the difference between companies that incrementally improve existing technology and companies that delete the technology entirely. One approach gets you slightly better results. The other approach gets you to Mars. What do you think? Is SpaceX's solution actually more reliable than traditional systems, or are they taking unnecessary risks by abandoning proven technology? Drop your thoughts below. If this breakdown gave you a new perspective on how radically different Starbase infrastructure really is, hit that like button and subscribe to New Space Review for the technical deep dives you won't find anywhere else. We're tracking every Tower 2 upgrade as SpaceX pushes toward their first V3 Starship launch. China just launched 88 rockets in a single year. That's more than double what they achieved 24 months ago, and the pace keeps accelerating. While SpaceX dominates with reusable boosters and rapid turnarounds, China quietly developed something different: a manufacturing system that treats rockets like products rolling off a car assembly line instead of handcrafted machines. How did they solve a problem that's stumped Western aerospace engineers for decades? And what happens when this production machine reaches full speed? The answer starts on December 20th.